Okay, so I think we can start, and today we have a very clear objective to finish any discussion on polynomial chaos expansion. We have to finish it by today because polynomial chaos expansion is in your homework. The deadline for which is what, 10th of October, 5th of October, right? So yes, so basically there will be no lecture before that. Today is the last lecture because the next week is holiday, midterm break, right? And we will next meet on what, 6th I think 6th of October is when we will meet next, which is Monday. Okay, so we'll wrap up polynomial chaos expansion, but the good news is that it should be easy to wrap up polynomial chaos expansion. The difficult part and the important parts are already done. So you're already done with the important parts, so it should not be very difficult to wrap up our discussion on polynomial chaos expansion today. So before we start, a quick recap. Till now, there have been 3 lectures on polynomial chaos expansion without explicitly talking about polynomial chaos expansion. The first lecture was a review of functional analysis, the Banach space, the Hilbert space primarily. The second lecture was that how orthogonal polynomial expansion in the Hilbert space can represent any function. That was the second lecture. And the third one was on inner product, quadrature, how to evaluate the quadrature, and so on and so forth. So primarily this have been our journey in polynomial chaos expansion till now. We have not talked about uncertainty explicitly, apart from the fact that x was a random variable with PDF fxx, inner product was using that fxx and all those things, but explicitly it was not there. Definitely there was nothing about reliability, and 100% there was nothing about surrogate modeling. Today all of this will be covered, and you will realize that whatever we discussed in the last 3 lectures, it will be just a plug and play of those things, and by just plug and play we will be able to solve or talk about polynomial chaos expansion and its application in uncertainty quantification, uncertainty propagation, and more importantly in the context of this course, in reliability analysis, right? So to start with, I mentioned something in the first lecture when we started polynomial chaos expansion within the first 5 minutes, and that was we are going to talk about 2 types of polynomial chaos expansion. Do you remember the names? Intrusive polynomial chaos expansion and non-intrusive polynomial chaos expansion, right? So we'll talk about PCE, and we'll talk about 2 types of PCE. One is intrusive, the other one is non-intrusive. These are the 2 things we are going to talk about, and we are going to talk about both of these today. Okay. What is intrusive PCE? Intrusive PCE is obviously PCE, and PCE does not change orthogonal polynomial expansion, but the unknown coefficients Ci of polynomial chaos expansion in intrusive PCE are determined by using the governing physics of the problem, by using the governing equation of the problem. So the governing equation is explicitly used. The governing equation is explicitly used. The knowledge is explicitly required for training the intrusive PCE. And that's why it is called intrusive, because you are intruding a model and you are using the physics that is governing that model. You are intruding a system and you are using the physics that is governing that system. In non-intrusive, you do not care about the physics of the problem. You generate data to a least square, find out the Ci. Okay, or you can do gallery, I mean the projection also. That also is possible, but yeah. So both of this. The maximum time will be required for intrusive, so we'll start with the intrusive PCE. Okay. So suppose we have a system governed by, and we are going to take a very simple system. Let's take this one, right? Dy by dt is equal to minus x1 y. Okay, where x1 is a random variable. Where x1 is a random variable. Okay. What kind of equation is this? Exponential decay, right? If you solve it, you will get an exponential decay. The solution will come like this. You can solve it analytically. We will not do that. I mean, you can solve it analytically if x1 is known. In this case, x1 is a random variable. But in any case, to solve this equation, you will need the initial condition. It's an initial value problem. So y at t equal to 0, and let's call it x2. So the initial condition is also random, right? And both of this, for the sake of our discussion, let us assume that x1 is Gaussian. I mean, I'm not writing mean and standard deviation. x2 is also Gaussian. Again, I'm not writing about the mean and standard deviation, that is not really needed. Okay. Now, with this problem, right? x1, looking at the equation, can you tell me about the practical range of x1? Greater than 0. If it is less than 0, that will become positive, and then it will not be a decay equation, right? So decay equation is like popular, how people, let's say some decay, right? Some species dies and decays, just like that, right? So x1 should be positive. We know that. In the ideal world, you will not model it as a Gaussian. Gaussian theoretically goes from minus infinite to plus infinite. So in the ideal world, you will model it something like a log normal kind of distribution, right? So that it is non-negative. But from a practical consideration, you can take it to be Gaussian, take the mean far away from 0 and take a very small standard deviation. So practically it will never go to 0 or less than 0, more specific, right? So practically you can take it Gaussian, but in theory you should not never take it Gaussian. I am taking it Gaussian because it's for the discussion sake. Okay. But if someone asks you what distribution should you use to model x1, your answer should not be Gaussian, right? It should be some non-negative distribution like log normal. x2, that can be negative positive. So x2 is kind of fine. That's the initial condition. Mostly it will be positive. Otherwise, from negative it will again start to go to too much negative. So generally it starts from positive and that thing. So again, x2 also will like it to be positive. So again, it should not be Gaussian theoretically. Practically, again, it can be Gaussian. Take somewhere away and you can manage. Okay. So anyways, this system has how many random variables? 2. We want to solve reliability ultimately. But for solving reliability, I will like to develop a machine learning, or in this case, surrogate model. A surrogate model that maps between, it should map at least between x and y. It should map between the random variable and the response, right? But in intrusive PCE, you do not only map from the random variable to the output. You map from all possible input variable to all possible output variable. So if I go by this philosophy, what should be my input? All input variable I talked about. So x1, x2 are inputs, random inputs, but along with that, there is one more input, which is t, time. So the input, my input will be x1, x2, t. Output will be y. So what we will have? So we want to learn y as a function of x1, x2 and t, right? Now, if things are in the Hilbert space, x1, x2 are Gaussian, so I should be able to write this F as a linear combination of orthogonal or orthonormal basis. What will be my orthonormal basis? The orthonormal basis for the Gaussian distribution, which is the Hermite polynomial. Because remember, this orthogonal basis depends on the distribution. So in that sense, it will be Hermite polynomial in this case, or to in a more generic case, you should first find out what polynomial to use by using some Gram-Schmidt transformation or whatever to find out those bases. Okay. So in PC, in polynomial chaos expansion, we know that y will be equal to summation I is equal to 0 to infinite, and this is an exact series. If I go up to infinite, Ci psi I and this is the most important thing. What have I done here? See, the polynomial basis, the orthogonal bases are only functions of the random variable, whereas the coefficient now is function of time. So I have separation of variable. I have separated out time and the stochastic variable, because the orthogonal basis only resides in the probabilistic space, in the X space. So the orthogonal basis cannot be function of time. The orthogonal basis should not change with time. They should only cater to the random variable in the system, because time is not random. So that Hilbert space thing is only applicable on X. However, the expression itself can change with time by changing the coefficients. So the coefficients will be function of time. And that's why the orthogonal basis catered to the random variable, whereas the coefficient catered to the time or to space. If it is a PD, then C will also be function of x and t. For a time spatio-temporal problem, C will be function of x and t. Okay. What have I done? Any question?
How do we know that in this situation we need to take C as a
in all situations.
Time and spatial.
But looking at the equation, what is the governing equation? Is there any space? If the equation was the governing equation is what? Where is space there? Y is state variable. Y is state variable. Space x coordinate, spatial coordinate will come only when it's a PDE.
So if y is a function of x and y, then like
Y is a function of x and y.
Like spatial variable.
If y is a function of x and y, then will it be a d or del? That is partial differential equation. So your equation will tell you, right? The equation will itself tell you whether if there is a del y by del x, the equation itself is telling you y is a function of x. If del y by del x does not exist, so there is no spatial variation, right? The equation itself will tell you it's an intrusive approach, which means that the equation has to be known to you, right? x1 can be a function of time, x. So you are talking about random process in that case. That's a random process. What you are saying, that let's say x is changing with time. It can be, but in that case you have to first discretize that time sequence into random variable. So there are things like Karuhan-Loeb expansion and all those things, which can be used to discretize a random, that is known as random process, or there can be a random field. We'll talk about it somewhere later. So if there is a random process or a random field, that means a random function. You need to discretize that random function into random variable first. And then this PCE is always a function of those random variable. I mean, in the sense that the orthogonal basis are function of the random variable. Okay. If x is function of time, then it's not Gaussian, random variable. Then your orthogonal basis is not Hilbert. I mean, it's not, I mean, Hilbert's, not Hilbert, I mean, Hermite. It's not Hermite. So things change, right? So we are only talking about random variable, not random process, not random field.
We are trying to substitute the limit state function inside of it now.
No, right now I have not defined any limit state function. But you are right, we will ultimately try to approximate a limit state function by a surrogate model. That is correct. In this example, there is no limit state function as of now. But you can imagine a limit state function will be what? Y greater than some or less than some threshold. So what will you do in that case? Remember I told you that in many cases, instead of surrogating the G, you surrogate the response. So in this case, I am surrogating the response. Keep that in mind that I am surrogating the response, not the limit state. Right? This is fine. Okay. So this was a simple expression I have done. I cannot work with this expression because it is an infinite series. So I'll have to approximate, I have to truncate it. So let's say I truncate it, which is approximately equal to summation I equal to 0 to number of bases. Let's use n CIT psi I x. Okay. I truncate it. Now it's a finite series. I can use it. Okay. What is known here? Psi is unknown. Right? Psis are known. The input variable x you can always get by sampling those random variables. So in that sense, that is known. The distribution is known. What is unknown? C is unknown. You want to find out C. In intrusive polynomial chaos expansion, we use the governing equation to find out C. We convert the governing equation, which is right now in terms of the state variable y, into coupled governing equation, deterministic, which is in terms of C. So we'll use that equation and this expression and convert that equation into coupled differential equations in terms of C, the unknown coefficient. And the unknown coefficient is function of time, so you will have dc by dt and all those things. How will you do that? I'll come to that now. But the bigger picture is that what we will want to do is to use that equation and the initial condition, combine it with this expression of y, and convert that somehow into coupled differential equations, which should allow us to find out C. And how many coupled differential equations will I need? N plus 1. 0 to n, so n plus 1. Right? How will you do that? It's very simple actually. I'll take this expression, substitute into the equation. I take this equation 2, let's call it, and substitute it into equation 1. So substituting into the governing equation. What do I get? The left side is dy by dt. dy is approximately equal to, so d dt of summation I equal to 0 to n CIT psi I x, right, is equal to minus x1 times y. Y was there. Y again is the same expression. Summation I is equal to 0 to n CIT psi I x. Simple. I am not touching the initial condition right now. We have to touch it eventually, but not right now. Okay. Now the left hand side, derivative of summation is equal to summation of derivatives. The derivative will go inside, and that is derivative is with respect to time. What is function of time? Only c. So the derivative will only be the function of, c will only be, you will take derivative of only c. So this implies summation ci dot t. Ci dot I am writing for shorthand notation. Psi ix. I'm removing I equal to 1, 0 to n. You know that it is there. Is equal to x1, I am pushing it inside. I will push the x1 inside the summation. The summation is over I, x1 does not have any index I, so x1 can just go inside, and I'll write it as minus summation I equal to 0 to n CIT, and this term will be x1 psi I x. Remember, x includes x1 and x2, by the way. So psi I has both x1 and x2, keep that in mind. So this gives me one equation. I need n plus 1 equations. What will I do? Galerkin projection. Remember anyone? What is Galerkin projection? You multiply by the basis and take inner product of both sides. So let's take one basis as an example. Let's take psi j. So I am taking psi j, multiplying on the both side and taking an inner product. Now you know inner product by now. We discussed it last lecture. You know how to take inner product. There will be quadrature coming soon. You can understand. Orthogonal basis we know. I have already used it. So those are the things that are now coming into picture. Whatever we discussed in the last 3 lectures, right? So what I will do is I'll multiply left hand side and right hand side by psi j and take the inner product. So that is like projecting, right? Inner product means projection. So that's why it is the Galerkin projection actually. So multiplying LHS and RHS by psi jx actually, and taking inner product. Right? First term, how will it look? See, I'm writing, you tell me whether you agree with it or not. Ci dot inner product of psi ix, psi jx, sum over I. You agree? Because Ci is not a function of x, so the inner product Ci will come outside because the integration is with respect to x, the random variable. Right? Any doubt on the left hand side? Right hand side. Tell me what will be the right hand side? Minus summation I equal to 0 to n CIT, and then inner product of x1 psi I comma psi j. Comma psi j.
For J also we will have some J1, 2, and something like that.
So this is for the jth basis I am doing it. This will give me one equation. I have to do it for all the bases. That's how I will get n plus 1 equations. This one I am doing for the jth one. So I will do one basis at a time. Each basis will give me one equation. Right? So that's why I'm using j. It's a jth basis. And this j will also vary from 1 to or 0 to n. Right? Left hand side, can you simplify? Cj dot. Cj dot. Because that is orthonormal basis. So everything else will go to 0. Only I equal to j will remain, that will be 1. And so Cj dot. So this implies Cj dot, it's a function of time, is equal to right hand side. Can you do anything about it? You cannot. You don't have any property. So what will you do? The sparse grid collocation, the quadrature, last time we discussed. If everything we can do, it's an inner product. Quadrature, which is the integration. Quadrature is for following an integration. So we were discussing that quadrature, if everything will be closed form, I would have not discussed about quadrature, right? One lecture I spent on quadrature. So obviously there will be terms like this which you cannot find out. So this inner product will remain as it is. You need to evaluate it. You cannot evaluate it analytically. So you have to use some numerical technique. And we talked about one of the good numerical techniques, which is the Smolyak quadrature, the sparse grid method. So you will use quadrature to evaluate that numerically, so but the right hand side will not change or not reduce. I mean, even the left hand side is not changing. Minus summation I equal to 0 to n Ci, it's a function of t, inner product of x1 psi 1 or psi I actually, x comma psi j x, and this is to be evaluated using quadrature. When you evaluate it using quadrature, it will take some form of summation of wi multiplied by x1 psi I x1 multiplied by psi j. So it will come as some summation form, because this inner product is what? Integration of the product of two things multiplied by the PDF. When you write in terms of quadrature, it will become summation and the inside term will remain as it is. We'll just take samples and do it, right? So it will become some summation, okay? So to be evaluated using quadrature. And let us assume when you let us call it let us call it Bij. Just a name. Let's call it Bij. So your equation now is then Cj dot is equal to minus summation over I Ci Bij. And this is one equation you are thinking, but j goes from 0, 1 to n. So what are you getting now? By the way, the best thing about this is that C, it is not a function of x. The random variables have been eliminated. There is no random variable now. It only involves, you are thinking that x1 is sitting there, but when you take the inner product, it takes derivative with respect to x. So it will vanish. It will not be a function of x. Whatever you integrate, that it is and put the limit, it cannot be a function of that. And there is a limit of that, right? The PDF has a limit, so it will be from that limit. So Bij will essentially become a constant kind of thing, okay? I mean, or some function of something, but it will not have random. It is not random. That's what I mean. Okay. So the best thing is that I have eliminated uncertainty from the system. And that is okay, because once I find Ci, I am going to plug that Ci into this expression. Not this expression. Where is that expression? This expression. I'm going to plug Ci into this expression, and my final y will be random. Y is still random, x is sitting there. C is not random, and that's why the differential equation that we use for finding out C is also not random. Okay. So this equation, this coupled equation, if you solve it, you will get Ci or Cj or Cj's n plus 1 Cj as a function of time only. How will you solve it? Use your favorite time integration scheme, Euler, Runge-Kutta, predictor, corrector, whatever you like, you use it, leapfrog, whatever you like, you can go ahead and use that any time integration scheme, and that will give you this Ci at some discretized time. You will not get it as a function of time, you will discretize it, time discretization, but you will get as many Ci as you want. You can make your time integration step smaller and smaller, you will get finer and finer Ci. Right? But you can only solve it if you know the initial condition. This is the initial value problem in C, and you cannot solve it without knowing the initial condition. So what will be the initial condition for C? You do not know that. Do you know the initial condition for C? It's not available, right? So you need it. You need the initial condition for C. How will you find the initial condition for C? The initial condition for y is given in this form. You write that y as a function of c and psi, but this time the c will be at t equal to 0. Again you will take inner product and that will give you c0, c1, c2, everything at t equal to 0. Let us do that.
These differential equations will be coupled. So can we apply those Rajikutta method and all this like on coupled differential equations?
Yeah.
But we have used only for a single equation.
What equation have you used for it for? Can you give me one example?
For the
For vibration
CFD.
CFD. CFD is first order. Have you done any course on the dynamics? You have done, right?
Yeah.
So you get mx double dot. There have you used this Rangakutta? Can you use this Rangakutta?
CFD we used transaction the fusion equation we have done.
Yeah, that's okay. So second order also what you do? You take it to be x1 and x2 two state variables and you make it a vector, right? And then you use it. This mx double dot plus cx dot, what you do? You make a state variable which is a vector. So in this case, c will become a vector of a state variable x or state variable c, which has n plus 1 elements. And then you will apply it on the vector. Okay, you have used it, I think. Even a second order equation becomes two first order equation. So in that sense, in the simplest equation, mx double dot plus kx, that becomes mx1 dot and then x2 dot, and that becomes, we have used it there, that becomes two state variable. So ultimately this equation is a single equation in form of vector, or it is n plus 1 scalar equation, however you like it. But that is applicable. All the time integration schemes are for first order equation. So as long as it is first order, you can use it. If it is second order, you have to convert it into first order. So in that case, the number of state variable increases, and that's all. Okay. Any doubt on this before I move on to the initial condition? Correct. So can you write down this in this inner product? How will it look? Integration of x1 psi 1 x multiplied by psi j x fxx dx, and the integration will go from some x, and it will do two integration, 1 over x1 over 1 over x2. This x is 2, remember that, and each one will have a limit. Let's take that limit as 1 to 2. Actually it will be from minus infinite to plus infinite. Now when you do this integration, will there be any x left after solving this integration? Integration of fx dx from a to b. Your answer, does it even have any integration? It will be a function of a and b, right? So it will be a function of some limits. So there will be no x remaining, right? Because we are solving an integration, whatever value you integrate out, that goes away and the limit stays. So that will happen here. Okay. Any question on this one? Then let us move to the initial condition. To solve this, IC, which is initial condition, is needed. Right? Everyone agrees IC is needed. Our original IC is y at t equal to 0 is equal to x2. Y at t equal to 0, you write it in terms of polynomial chaos expansion. Summation Ci at t equal to 0 multiplied by psi I x I equal to 0 to n is equal to x2 multiplied by psi j on both sides, take a inner product, multiplied by psi j, take inner product. What will you get? Left hand side will only have cj, right? So, and the right hand side will have some inner product which will give you some number, and that number will be your initial condition for that coefficient. So multiplying by psi j and taking inner product. So the left hand side you will only have Cj at t equal to 0, and the right hand side will have inner product of x2 comma psi jx, and again this will be some number, this will be some number, and this again you will do n plus 1 number of times to get n plus 1 initial conditions. So you now have n equations or n plus 1 equations, n plus 1 initial condition, you can now solve it, right? You can now solve it. Once you solve it, what do you get? C, all the C's. Once you get C's, you will go and put it here, the right bottom expression, CIT psi ix, you'll put it here. That will give you y, which is random because psi I is still random, right? So that is your surrogate for the solution field. Now, if you have a threshold, you subtract it or add it, whatever it is, do a Monte Carlo sampling over that, it's trivial. Sample X and do that, even if you can think of doing it analytically, we have analytical expression now, and find out the probability of failure. This is the intrusive polynomial chaos expansion. It is intrusive because it uses the governing equation, right? That's why it is intrusive. Let me repeat the whole thing once more. Yeah, go ahead. So it will not be difficult to derive this, it will be difficult to solve this, obviously, without a doubt. If the left hand side is nonlinear, it will be difficult. Even there also you will keep doing those inner quadratures. Obviously it is difficult, and that's why it is not that popular, but it is much more accurate. If you can use it, it will be highly accurate. I mean, you cannot get this kind of accuracy with non-intrusive, let's put it this way, and also it is learning the whole field. I mean, in this case time, but for us other problem, for the response, the stochastic response over the whole spatial field and temporal field in one go. You tell me, how will you choose it? You cannot choose it. So what will you do? How do you choose the finite element mesh? Same thing. You will keep on increasing it and see whether there is a change or not. Convergence study. And you can do convergence study because this is in the Hilbert space, which is complete inner product space, which means a sequence that looks like converging is converging. That's why that was important in Hilbert space. Okay, so that Cauchy's sequence I introduced because of this only. How will you find out this n? Okay, I'll repeat the whole process once more before I move to the non-intrusive one, which will take me 5 minutes. Non-intrusive you already know. Okay, so we in the previous 3 lectures we talked about functional space, and we saw that how Hilbert space, or did not saw, I tell you how Hilbert space has all the properties of Rn space, and similarly as a vector can be represented summation of bases. In Hilbert space a function can be represented, any function in Hilbert space can be represented as summation of linear combination of bases, but the number of bases is infinite, and that expansion is an orthogonal expansion. That expansion is known as the polynomial chaos expansion. We talked about it, right? The other thing we talked about is the inner product space, what is the inner product, generalized inner product, and all those things, right? We also talked about quadrature and how an inner product or any integration can be evaluated kind of efficiently in dimension up to 10 or 20 using quadrature, right? At least the Smolak quadrature. We talked about that. So today, the first thing we discussed is how this will be used for uncertainty quantification and primarily for reliability analysis. Now there are 2 variants. We have till now discussed only one variant, which is the intrusive polynomial chaos expansion. In intrusive, the name intrusive comes from the fact that it requires the governing equation, so it is as if you are intruding the system. So that's why the name intrusive. What you do is the governing equation you need to know. You assume the solution as a linear combination of the bases. You truncate it, make it finite. You always do that. And then you substitute that equation into the governing equation. And then take Galerkin projection or do an inner product by multiplying with a psi, a basis. That's a Galerkin projection, right? When you do a Galerkin projection, do that thing, you end up with equation, deterministic equation. Till now the equation was stochastic because there was stochasticity, randomness in the equation. This equation now is coupled but is deterministic. So you end up with deterministic equation, you end up with deterministic initial condition, use them, use your favorite numerical integrator, time integrator, solve it, you get Ci as a function of time. Take those Ci's, go back to the original expansion, put those Ci's. Psi you already know, that is your approximate y, which is actually quite accurate. Okay, so you get your y. Now, what you want to do? You will want to do reliability. One way is go and integrate it within the threshold limit. May be difficult, may not be difficult, depends on x and depend on this. In the worst case scenario, just sample it. It's a linear equation, right? There is no differential, nothing. Just factorize it, draw up billion samples, do it. That's your reliability. And that the billion samples can be done in 2 minutes, 3 minutes. That's all. If your memory is enough. If your otherwise, do a million. That's also fine. Right? That's what intrusive PCE is. Any question on the intrusive PCE part? After you know this, after you find out C, then you will sample. If you otherwise you don't know C, right? So the beauty of this is that coding this is very simple. Given you have a code that can do quadrature and give you integration. Given you have a code that can give you orthogonal polynomial. And given that you have done the derivation and simplified the equation. Because to go from this equation, dy by dt is equal to minus x1 of y, to this equation, cj dot is equal to summation over I, ci, bij is your job. Computer will not do that. So you have to derive that. Once you have derived that, then it's usual numerical technique. But this derivation is to be done, and it is to be, as the problem changes, this derivation changes, the form might change a little bit, and you have to do this. So this derivation you have to do. Once you have done this derivation, coding is simple, given whatever I said is available to you. Okay. So there is one problem given in the homework on intrusive PCE. You have to use all of those what we have talked till now. It is problems. Intrusive means it requires the physics. That means it is a function of physics. If the physics changes, go and derive it. Okay. That is what intrusive means. And because it is specific, it is highly accurate. It's always right. If I specialize in a subject, I will have much more expertise than something that does everything. Same thing holds for surrogate modeling. Okay. Non-intrusive. 3 minutes I'll take. Okay, I'll take 5 minutes. I have 5 minutes, right? Let's say. Non-intrusive PCE. What is non-intrusive PCE? It is a PCE that does not require the physics of the problem. You give him the data and that's enough. So the easiest way to think about it is it's a linear regression problem. A linear regression problem with polynomial chaos basis. That is all. I repeat, what is non-intrusive PCE? Remember, this still remains same. The objective is still the same. You want to find out C, right? In non-intrusive PCE, you do not care about the physics of the problem. You really don't. What you care about is to find out C. And the easiest way you can think of finding out C is just do a linear regression. It's a linear regression problem where your basis function are the orthogonal basis. So it's basically your linear regression code. If you have it, just change the basis to orthogonal polynomial. That's your non-intrusive polynomial chaos expansion. So remember, we talked about linear regression in response surface method. We already talked about it, right? In response surface method, we said that y was equal to w transpose x, right? Or if I have to write it in terms of vector, then y is equal to x is a matrix multiplied by w. We talked about it, right? And then we said that w is equal to x transpose x inverse x transpose y. This is known as pseudo inverse. You remember that, right? Correct? So in this case, what will happen? Now this was for linear regression. Now let's talk about non-intrusive PCE. Now it's not a function of time any longer. C is C. C is mapping between x and y. There is no time. It is not learning over the all temporal field or anything like that. Okay. So what you will do? Your y will be w transpose psi x, or rather in this form it will be y is equal to capital psi, which is a matrix, times w, which is a vector, right? And this is of orthogonal basis, which are the same as what if it is Gaussian, then it is Hermite. If the variable is uniform, it's Legendre, and all those things remains. This w is your C that you want to find out. What is your C then? Pseudo inverse of psi multiplied by y, which is psi transpose psi inverse psi transpose y. Done. This is a non-intrusive PCE. It's linear regression. There is another type of non-intrusive PCE which you can do by doing the inner product. Think about it on your own. Okay. That instead of using least square, is there any other way you can find out C? Instead of using least square, can you use projection? Remember I told you that find out C, you can do a projection some lectures ahead, some lectures before, that you can do the projection of total function onto a basis and that will give you C. So think about how you can use it to find C also in a non-intrusive manner. You can. Think about it. Okay. It's easy actually. You will just find at the quadrature point, you will actually evaluate the function and then use quadrature to find out the dot product that will give you C. Okay, so you can even do that also, but this is the more popular one. Do the linear regression, but the bottleneck, the bottom line, not bottleneck, the bottom line is that non-intrusive PC is like a usual data-driven technique, you know. Intrusive PC is more involved, but it is much more accurate. So the way I see it, I look at intrusive PC as similar to physics-informed neural network, whereas I see as this non-intrusive as data-driven neural network. If you have to draw a parallel, and this non-intrusive PC is there since 90s or 2000. It became popular in 2001 by the work of Dongbing Zhu and George Karnitakis. But they did not call it physics-informed PC at that point. If it was developed today, people would have called it physics-informed PC. The name physics-informed was not that popular at that time. That's all. Okay. And this is much more accurate than a physics-informed neural network actually. Much more accurate, and it is actually solving stochastic differential equation. Pin solve deterministic. Much more. Pin solve one equation, right? Deterministic. It solves stochastic differential equation. People are using it. There is a paper in last month, polynomial chaos expansion as the operator that outperforms all neural operators. There's a paper last month. People are still working on it. Okay. So it's a very powerful technique. The fact that you can go to the Hilbert space or the orthogonal basis and learn things is a very powerful idea. That idea is very powerful. It gives the best convergence. The only problem is number of bases grows exponentially, so it cannot handle large number of variables. That's the main bottleneck. If you have 1,000 variable, 10,000 variable, it will not work. Neural network might work. So that's the strength of neural network, because there is no inversion in neural network. Here you see this inversion and all those things which are cubic, right? So as the number of bases increases, it does not work as simple as that. So that's the bottleneck. Okay. Otherwise, this is a very powerful technique. People have used, there is a polynomial neural network where they try to use the W transpose X, that is polynomial basis, inside the neural network. There are work on that. But this is already enough. So that is like overkill and not needed anymore. I have not seen any case where that is needed actually. To reduce the
because in a PC is much more accurate. The neural network neural operator method is not that accurate. So combination of those two.
So you don't need that combination. People have combined it with PCA. So use PCA to reduce the input dimensionality, and then use PCE on the reduced space.
PCA has a disadvantage that it will lose a lot of information.
Correct.
If there is
But
redundancy there.
correct. But use autoencoder to reduce that space. Use a nonlinear reducer model. The idea is that your bottleneck is dimension. Reduce it if possible. Active subspace. Nabin's work, right? So all of those are modified from this. Okay. Anyways, this is a very powerful technique, and without being powerful, something cannot survive for 25 years. 2001, I said it became popular, proposed even before that. Today is 2025, still people are developing algorithms for this. So it is so powerful. Okay. Any question? If not, we are done with PCE. Next thing we'll do is Gaussian process, which is after the midterm break. So I'm expecting 3 lectures, 2 on Gaussian process, maybe 1 on to conclude surrogate modeling. So in 3 to 4 lectures, we'll be done with surrogate modeling, and then we'll go to advanced topics in reliability. Okay. What is that? NI, non-intrusive. I was lazy to write the whole thing, so I write NI. And then my pen moved, so it becomes something else, some Chinese. Okay. Yeah.
It can be used for stochastic. How people are using this thing as stochastic?
It is stochastic, right? This equation is stochastic. Where is that equation? This is a random equation. There is random variable sitting there. X1 and X2 are sitting there. I'm not talking about stochastic differential equation in the sense of Brownian motion and all those things, but because there is randomness here. So that's why the solution is a stochastic process. Y is a function of random variable and time. So the solution is a stochastic process. Y is a stochastic process. It changes with time and it is random.
Then this kind of problem will be very useful because Pins has a problem that it can't deal with different boundary conditions.
It can easily. It does. It already does. People have been doing it for years. Okay. Okay. Thank you. We'll meet after the break. Okay.